When a multimeter's function or range switch is set to 200 volts alternating current, the reading obtained across the terminals of a fuse or circuit breaker depends on the condition of that fuse or breaker. Let's firstly consider a good fuse or circuit breaker in a 120 volts alternating current line. In this scenario, the multimeter will read 0 volts alternating current. The reason for this 0 volts reading is because a good fuse or circuit breaker, when functioning correctly, offers very low resistance to the flow of electrical current. Consequently, there is no significant voltage drop across its terminals. Voltage drop is the reduction in voltage as current flows through an electrical circuit. It occurs due to the impedance, including resistance, of the wires, connectors, and other components in the circuit. In simpler terms, voltage drop is the amount of electrical potential energy lost as current moves through a circuit. Since the fuse or breaker presents minimal resistance, the voltage on one side is virtually the same as the voltage on the other side, resulting in a negligible voltage difference, hence the 0 volts reading. Secondly, let's examine the case of a blown fuse or a tripped circuit breaker in a 120 volts alternating current line. In this situation, a multimeter set to 200 volts alternating current will also indicate 0 volts alternating current when measured directly across the terminals of the fuse or breaker. While it might seem counterintuitive that both a good and a blown fuse can result in the same reading, the underlying reasons are different. A blown fuse or a tripped circuit breaker introduces a break in the circuit, creating a very high resistance, practically an open circuit. Ideally, an open circuit means infinite resistance. Due to this extremely high resistance, almost all of the voltage drop occurs across the blown fuse or tripped breaker. However, because the multimeter is connected directly across the terminals of this high resistance element, it measures the voltage potential only at that point. On either side of the break there is voltage, but the leads measure the voltage from either side of the gap and thus zero potential. To effectively troubleshoot electrical circuits using a multimeter, understanding these principles is important. To diagnose a blown fuse or tripped breaker effectively, one must measure the voltage at different points in the circuit relative to a common ground to isolate where the voltage is present and where it is lost. For example, measuring the voltage on the supply side of the fuse and comparing it to the load side. If voltage is present on the supply side but absent on the load side, this confirms the fuse is blown or the breaker is tripped. It is also important to choose the correct voltage range on the multimeter. Although in both scenarios outlined, a 200 volts alternating current range is suitable for measuring a 120 volts alternating current circuit, selecting an appropriate range is vital for accurate readings. Using a range that is too high might not provide sufficient resolution for detecting small voltage drops, while using a range that is too low could damage the multimeter or provide inaccurate readings. Electrical safety is paramount when working with electrical circuits. Always energize the circuit before performing any measurements or repairs whenever possible. If working on a live circuit is unavoidable, use appropriate personal protective equipment such as insulated gloves and eye protection, and follow safe work practices to prevent electrical shock or arc flash. Never assume a circuit is de-energized until it has been properly tested with a reliable voltage meter. Furthermore, it is essential to understand the limitations of a multimeter. A multimeter is a valuable tool for electrical troubleshooting, but it does not replace a thorough understanding of electrical principles and safe work practices. Always consult the manufacturer's instructions for the multimeter and follow recommended procedures for accurate and safe operation. In summary, a multimeter set to 200 volts alternating current will read 0 volts alternating current across a good fuse or circuit breaker in a 120 volts alternating current line due to low resistance and minimal voltage drop. It will also read 0 volts alternating current across a blown fuse or tripped circuit breaker due to the very high resistance and the nature of the measurement being taken directly across the break in the circuit. Remember to prioritize safety, use appropriate equipment, and apply sound electrical knowledge when working with electrical circuits. Consider this. Electrical circuits function based on fundamental principles that include firstly, voltage, which is the electrical potential difference or pressure that drives the flow of charge. Secondly, current, which is the rate of flow of electrical charge typically measured in amps. Thirdly, resistance, which is the opposition to the flow of current measured in ohms. These three quantities are related by Ohm's law, which states that voltage equals current multiplied by resistance. Understanding this relationship is crucial for analyzing and troubleshooting electrical circuits. For example, if you know the voltage and resistance in a circuit, you can calculate the current using Ohm's law. Conversely, if you know the voltage and current, you can calculate the resistance. When current flows through a resistance, it generates heat. This is known as the Joule effect, and it is the principle behind many electrical heating devices, such as toasters and electric heaters. The amount of heat generated is proportional to the square of the current multiplied by the resistance. Fuses and circuit breakers are overcurrent protection devices designed to protect electrical circuits from damage due to excessive current flow. A fuse is a sacrificial device that contains a thin wire or strip of metal that melts and breaks the circuit when the current exceeds a certain level. A circuit breaker is a reusable device that automatically interrupts the circuit when it detects an overcurrent condition. Circuit breakers typically use a bimetallic strip or an electromagnet to trip the breaker and open the circuit. Electrical circuits can be wired in series or parallel configurations. In a series circuit, the components are connected end to end, so the same current flows through all of the components. The total resistance in a series circuit is the sum of the individual resistances. In a parallel circuit, the components are connected side by side, so the voltage is the same across all of the components. The total current in a parallel circuit is the sum of the individual currents. Most household and commercial electrical circuits are wired in parallel so that each device receives the same voltage. Electrical power is the rate at which electrical energy is transferred. It is measured in watts and is equal to the voltage multiplied by the current. The amount of power consumed by an electrical device depends on its voltage and current requirements. For example, a 100 watts light bulb consumes 100 watts of power when connected to a 120 volts alternating current source. Electrical energy is the total amount of electrical work done over a period of time. It is measured in kilowatt hours and is equal to the power multiplied by the time. Electrical energy is what you pay for on your electricity bill. Understanding basic electrical concepts is essential for anyone working with electrical circuits. Always follow safe work practices and consult with a qualified electrician if you have any questions or concerns. Now consider voltage drop calculations. Voltage drop is an important consideration in electrical circuit design and installation. Excessive voltage drop can cause equipment to malfunction, reduce the efficiency of electrical systems, and even pose a safety hazard. Voltage drop is calculated using Ohm's law, which states that voltage drop is equal to the current multiplied by the resistance of the conductor. The resistance of a conductor depends on its material, length, and cross-sectional area. Longer conductors have higher resistance, and thinner conductors have higher resistance. Different materials have different resistivities, which is a measure of how much they resist the flow of current. Copper and aluminum are commonly used as conductors in electrical wiring because they have low resistivities. The National Electrical Code, or NEC, provides guidelines for calculating voltage drop in electrical circuits. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. Branch circuits are the circuits that supply power to individual outlets and lighting fixtures, while feeders are the circuits that supply power to branch circuits. To calculate voltage drop, you need to know the current flowing through the circuit, the length of the conductor, and the resistance of the conductor per unit length. The resistance of the conductor can be obtained from tables in the NEC or from the manufacturer's specifications. Once you have these values, you can use Ohm's law to calculate the voltage drop. If the calculated voltage drop exceeds the recommended limits, you need to increase the size of the conductor or reduce the length of the circuit. Increasing the size of the conductor reduces its resistance, while reducing the length of the circuit reduces the total resistance. Other factors that can affect voltage drop include the temperature of the conductor and the presence of harmonics in the electrical system. High temperatures increase the resistance of the conductor, while harmonics can cause additional voltage drop due to increased current flow. When designing and installing electrical circuits, it is important to consider voltage drop to ensure that equipment operates properly and safely. Use the NEC guidelines and consult with a qualified electrician to ensure that your electrical circuits meet the required standards. Understanding grounding and bonding is also important. Grounding and bonding are essential safety measures in electrical systems. Grounding provides a path for fault current to flow back to the source, tripping the circuit breaker or blowing the fuse and preventing electrical shock. Bonding connects all metal parts of an electrical system together to create a low impedance path for fault current. Grounding and bonding work together to protect people from electrical shock and to prevent damage to equipment. Grounding is typically achieved by connecting the neutral conductor of the electrical system to a grounding electrode, such as a ground rod or a metal water pipe. The grounding electrode provides a connection to the earth, which serves as a reference point for the electrical system. Bonding is typically achieved by connecting all metal parts of the electrical system together with bonding conductors, such as wires or straps. These bonding conductors create a low impedance path for fault current, ensuring that the circuit breaker or fuse will trip quickly in the event of a fault. The NEC provides detailed requirements for grounding and bonding in electrical systems. These requirements specify the size and type of grounding and bonding conductors, as well as the methods for connecting them. It is important to follow the NEC requirements carefully to ensure that your electrical system is properly grounded and bonded. Improper grounding and bonding can create a dangerous situation that could lead to electrical shock or fire. In addition to protecting people from electrical shock, grounding and bonding also help to protect equipment from damage due to voltage surges and other electrical disturbances. A properly grounded and bonded electrical system provides a stable reference point for voltage, which helps to prevent voltage surges from damaging sensitive electronic equipment. When working with electrical systems, it is important to understand the principles of grounding and bonding and to follow the NEC requirements carefully. If you have any questions or concerns about grounding and bonding, consult with a qualified electrician. Additionally, it is beneficial to comprehend circuit breaker operation. Circuit breakers are essential components of electrical systems, providing protection against overcurrents and short circuits. They are designed to interrupt the flow of current when it exceeds a predetermined level, preventing damage to equipment and reducing the risk of fire. Circuit breakers come in various types and sizes, each designed for specific applications and current ratings. Understanding how circuit breakers work is crucial for ensuring the safety and reliability of electrical systems. There are two main types of circuit breakers: firstly, thermal circuit breakers, and secondly, magnetic circuit breakers. Thermal circuit breakers use a bimetallic strip that bends when heated by excessive current. When the strip bends sufficiently, it trips the breaker and interrupts the circuit. Magnetic circuit breakers use an electromagnet that trips the breaker when the current exceeds a certain level. Some circuit breakers combine both thermal and magnetic elements for enhanced protection. When a circuit breaker trips, it is important to identify the cause of the overcurrent or short circuit before resetting the breaker. Simply resetting the breaker without addressing the underlying problem can lead to a recurrence of the issue and potentially damage the equipment or create a safety hazard. Overcurrents can be caused by various factors, such as overloaded circuits, short circuits, or ground faults. An overloaded circuit occurs when too many devices are connected to the same circuit, drawing more current than the circuit is designed to handle. A short circuit occurs when there is a direct connection between two conductors with different potentials, such as a hot wire and a neutral wire. A ground fault occurs when there is an unintended connection between a hot wire and a grounded surface. To troubleshoot a tripped circuit breaker, start by identifying the circuit that the breaker protects and disconnecting any devices that are connected to that circuit. Then check the circuit for any signs of damage or overheating. If you find any damage, repair it before resetting the breaker. If you do not find any damage, try resetting the breaker and reconnecting the devices one at a time, monitoring the current draw of each device to see if any of them are causing the overcurrent. If the breaker trips again, you may need to consult with a qualified electrician to diagnose and repair the problem. Circuit breakers are an essential safety component of electrical systems, and understanding how they work is crucial for ensuring the safety and reliability of your electrical installations. Always follow safe work practices and consult with a qualified electrician if you have any questions or concerns about circuit breakers or electrical systems.